I am Kumar Tanmay. I am a final year undergraduate student in the Department of Electrical Engineering enrolled in its BTech course of Instrumentation Engineering. I am doing my bachelor's term project titled Medical Tube Abnormality Detection in Chest X-rays using Deep Learning under the supervision of Professor Pavitra Mitra of the Department of Computer Science and Engineering. Medical tubes are life-saving equipments which are inserted into the human body for various purposes like breathing, passing food and medication to the required regions, and heart monitoring. Severe complications can occur due to any malpositioned tube and sometimes even death. In the chest X-ray shown here, we can see that the endotracheal tube has been wrongly placed near the tracheal junction, which can cause the damage to the lungs. The traditional way of detecting any tube malpositions is by manually looking at the chest X-ray. The aim of this project is to detect any abnormal position of the endotracheal tube, nasogastric tube, central venous catheter, and Swan-Ganz catheter given a chest X-ray automatically. The entire project is hence divided into three parts. The first is the classification of chest X-rays on the basis of the presence of a tube. The second is the semantic segmentation of tubes, their tips, reference anatomical regions, and ideal tip regions. The final part of the project is the detection of any abnormality detection with the help of different segmentation models trained in the previous stage. We worked on two datasets. The first is the Ranzer dataset, which is a publicly available Kaggle dataset, and the second is the privately owned Cure AI dataset. Tube classification involves detecting the presence of the tube in chest X-rays. The task can be used to filter out the chest X-rays containing tubes from those which don't have any tubes. We worked on the binary classification, which predicts results for a single tube only, and the multi-level classification, which predicts results for multiple tubes simultaneously. Here is the schematic diagram of a multi-level classification using CNN architecture. We experimented on different CNN backbones like SemNASnet, RegNet, ResNet, ResNext, and EfficientNet, etc. In this slide, we can see the results and important plots for the Swan-Ganz catheters, binary and multi-label classifiers having SemNASnet 050 as a CNN backbone. The area under the curve of the receiver operating characteristics graph is a useful metric to evaluate the performances of the classifier models. Other metrics like sensitivity, specificity, negative predictive values, positive predictive values, and J-fit index graph plotted against various threshold values helps to judge the model performances effectively. Here we can see that the AUC score of a multi-label classifier performs better than the binary classifier as the multi-label classifier models are trained taking into consideration all the tubes simultaneously, which helps them to learn better distinctive features compared to the binary classifier which is trained for predicting for the prediction of a single individual tube. Semantic segmentation is the task of clustering parts of an image together that belong to the same object class. We have used UNet and UNet++ based segmentation architectures with different CNN backbones. These architectures are widely used for biomedical segmentation. Here is the schematic diagram of the UNet architecture, which has an encoder to downsample the chest X-ray input into the feature vector representation and a decoder to upsample the feature vector representation to a binary mask image. During the downsampling, a lot of information is lost. Hence, to regain back that information, there are skip pathways from the encoder feature map to its symmetric decoder feature map, which helps to provide more information to the decoder part for upsampling. UNet++ is a modified version of UNet which additionally have dense CNN blocks in the skip pathways. These are some of the results of the segmentation models trained by us. These figures show the image of the chest X-ray, the actual and the predicted mask of the tube, tip, or anatomical regions. The average intersection over union score for tubes lie between 0.6 to 0.85 for large anatomical regions above zero point 0.8 and for small regions between zero point 0.1 to zero point 0.5. These segmentation will now be used for the final task of tube abnormality detection. Here is the tube abnormality detection using the student-teacher approach. First, a teacher model is trained using three inputs, which are the chest X-ray, tube mask, and anatomical region mask. Then a student model is trained with the same CNN backbone as that of the teacher model, but with a single input, which is a chest X-ray. In order to transfer dark knowledge stored in the teacher model to the student model, the feature loss function defined for training the student model involves a weighted average of the feature loss between the feature maps of the student and teacher models and the cross entropy loss between the ground truth label and the prediction of the student. Both the teacher and student perform better than the baseline model, which has the same CNN architecture with single input and is trained using cross entropy loss. AUC ROC is used to evaluate the model. Here is the abnormality detection using reference anatomical regions for each tube. In the schematic diagram, we can see that the segmentation models of cavo-arterial junction and carina are used to detect abnormalities in the central venous catheter tip position. For endotracheal tube, carina segmentation is used, whereas for nasogastric tube position, gastroesophageal junction segmentation is used. The Euclidean distance helps to find the spacing between the tips and the reference anatomical regions. The results using this method are better than that of the student-teacher approach. We have used F1 score, recall, and precision values to evaluate the method. Here is the tube abnormality detection using the ideal tip location. If the actual tip lies within 1 centimeter of the ideal tip position, then it is considered a normal position, else an abnormal position. These ideal and actual tip mask image is predicted by the respective segmentation models, and the distance can be found out using the blob distancing algorithm. This method of abnormality detection works fairly well compared to the previous two approaches. The future work will involve using a YNet architecture as a common architecture for both classification and segmentation. Ideal tip target region can be used as a better segmentation label compared to the ideal tip location. Also, higher resolution images can be used as input for better results. We can also fine-tune the models which are already pre-trained on large chest X-ray data sets for better representation feature learning, and self-supervised learning can also be used for representation learning as the large unlabeled chest X-ray data sets are easily available. Finally, we are concluding with some important findings. Some models face the problem of overfitting due to the lack of sufficient data. Subnasnet 050 as CNN backbone performs quite better than others in most of the classification tasks. UNet++ architectures performs better than UNet architecture. Both student and teacher models perform better than the baseline model. Tip abnormality detection using both reference anatomical regions and ideal tip gives good results. Automatic detection of any misplacement in tube position can help save severe complications and sometimes even death. Finally, we are planning to submit the modified version of this paper to the Winter Conference on Applications of Computer Vision 2023. Thank you.